Dear students, now we are going to see the next heat treatment process, that is the precipitation hardening or edge hardening. So dear students, this mechanism is actually very interesting and which you can find in the non-ferrous alloys here, that is the aluminum alloys. Dear students, this process was started in the laboratory of Alfred Wilm, who was working of the strengthening of the aluminum alloys, and he was also trying to generate the new aluminum alloy. This Alfred Wilm was having the background of steel, and he was knowing that when the steel is heated and it is quenched, it gets hardens. And the same query or same doubt was in his mind that whether the aluminum, for aluminum alloy also, it is same. So let us visit the Alfred Wilm laboratory. So what was this Wilm having? The specimen that he had, it contains 3.5% to 5.5% of copper in aluminum. Rest of what? Aluminum. So in the aluminum matrix, the copper percentage from 3.5 to 5.5%. And of course, what is the general heat treatment process that we are having? So he heat this specimen, hold it at particular time, and he quenched it. So this is temperature versus time. So he heat it, hold, and cool, or here because we are trying to form the martensite, of course it is quenched, and after quenching he measured the hardness of the specimen. But what was the observation? The observation that the hardness is actually lesser than the original specimen hardness. So original से भी क्या था, hardness कम था. So this Wilm was not so happy man at that time, because he was expecting that the aluminum also will behave like the steel, but it was his wrong thinking, isn't it? So, but at the same time he was the determined scientist, and he was several variables on his hands. So at which quenching rate we quenched, at what temperature we hold, so many variables actually was in his hand, and he was knowing how to use all these variables. So the one thing is clear, that if you want the martensite, you have to heat the above the austenitic temperature range, and to for the martensite it is very necessary to quench the such a rate that the cooling curve is definitely bypass the nose of TTT curve, isn't it? So he varied, he used this variable for the quenching, that is he varied all the possible quenching rates or cooling rates, and also he varied the composition, but the results was same. Because he was not getting any increase in the hardness of the specimen. So actually one Saturday morning when he was conducting his experiments in his laboratory, so as usual he heat the samples, then he hold it for, he decided temperatures, and he just cooled it or quenched it. But before that he looked outside his window and found that it was a very sunny day, and he was a lover of sailing. So what he did, he left this experiment as it is and he went for the sailing. And after this weekend, when he come back on the Monday, he again resumed his experiment. So whatever the work he left with, he started from that. Actually he heated that piece, hold it for temperature, certain temperature, and quenched. So when he measured, because after some time, after 2 days he came, and on Monday when he measured the hardness, so the hardness he observed that Hardness was increased. Now he was a very happy man, isn't it? So whatever the heat treatment we are generally following, heating, holding and quenching, isn't it? To get the martensite, actually I am using the word quenching. So definitely after some time when you quench and you left that specimen as it is for a particular period of time, so definitely you will get the increase in the hardness, isn't it? So actually he was very happy man at that time. Then he again repeated the experiments and he developed the literature for that process, actually what is happening there. So in around 1901 this process was done and he gave the name for this process as the edge hardening. What the name he is given? The process name was edge hardening, and this process and this phenomena he patented in 1906. 1906 में उसने ये प्रोसेस को क्या अपने नाम पे पेटेंट किया. नॉट ओनली द प्रोसेस, आल्सो दिस एलॉय. कौन सा एलॉय? एल्यूमिनियम कॉपर एलॉय. He patented his this alloy as well as this process which is known as edge hardening. So actually what he had the observations. Okay, so suppose after martensite formation I am having this certain hardness. So on y-axis I am plotting the hardness H, and on x-axis I am having here the time. So what the graph we can get here, see the graph will be like this. Okay, so see as the time goes on increasing after hardness, so this is hardness at the time of quenching. So after that when the time goes on increasing, see the hardness goes on increasing, isn't it? This was the observation. So this is what period? This is actually aging period. This is the aging, isn't it? This is the aging period. This is the aging. At this highest point we are getting the highest hardness, that is the peak hardness, if I name it as HP, for which time? That is peak time TP, isn't it? And after this time you can observe that the hardness again goes on decreasing. So this is what he gave the name, that this time period, or this is the over aging. This is the over aging. So let us see actually what we can have. So dear students, if you look at this process, we must have to plot the phase diagram, isn't it? And actually the Wilhelm was very clever scientist, so he was knowing that the theme of the subject material science or metallurgy is nothing but the properties of the material are depend upon the structure of the material. So he developed the many structures and he observed that what actually changed in the structure causing this increase in hardness. But again he was get surprised. He was astonished that after seeing that there was actually no change in any structure, any microstructure of the specimen. Okay, there was no any change in the microstructure. Then how this hardness gets increased? That was a very big question. Or for this increases hardness, there was no any structural change. How it is actually get happen? It was question in his mind. Let us look the phase diagram. For that reason we have to see the phase diagram now. So if you see the phase diagram of aluminum and copper, let us see this. So let us see actually here what actually happened, because see again microstructure also not showing any kind of change, but hardness, yes, hardness goes on increasing. So if you have here this phase diagram, not completely drawing this, so this is the liquid, you can have the eutectic reaction here. This is the alpha, that is interstitial solid solution of copper. Here is alpha plus liquid. Here it is 5.5%, 33%, 55%. This is the theta, that is the intermetallic compound of this aluminum and copper, that is Al2Cu. This is liquid plus theta, and here we are having this alpha plus theta. Now this is of course the melting point of aluminum, 660 degrees centigrade. This is 550 degree centigrade. Okay, so of course this is 0% copper, this is 100% aluminum. So this is interstitial solid solution of aluminum, isn't it? And this is weight percentage of copper here. Here 100% copper and 0% aluminum. So see here, this alpha is what? Substitutional solid solution. Theta is intermetallic compound, that is aluminum to copper 1. So by atomic weight percent, how much copper is there? Atomic weight percent, copper will be 33%. Yes or no? This is 1/3 of this compound, 1 copper is there. So see here, we are having this line. This is the solidus line. This is the solidus. And this line is the solvus line. So see, we are having, suppose here this temperature is what? D solidus, and this temperature is T solvus. Okay, so we are having this Will alloy here, and now let us say my alloy is at this temperature, that is say this is say the theta 1, this is, say I am taking here theta 2. Theta 1 is the temperature on solidus, and theta 2 is the temperature of solvus line, and this, that is our alpha at temperature theta 3, that is completely solvus, isn't it? So it is completely solid solution. So here, if I cool this alpha from this theta 3, I'm so sorry, phase is theta, I'm right here temperature as T1, this is T2, and this is T3. Okay, so see, when we cool this alpha below this solvus line, if we cool this alpha below the solvus line, so what is going to happen? So of course alpha is going to decompose into this alpha plus theta, isn't it? So here from this alpha, which is known as the supersaturated alpha, which is the supersaturated alpha, when it cooled below this solvus line, this is the solvus line, so what we are going to get? This alpha plus theta, and this alpha is what? Actually saturated alpha, and the theta is actually our precipitate, isn't it? So actually, if you see, if you want to have at any temperature range what is the composition of copper in this alpha, then what we can do, we can simply have to draw the tie line. At any temperature, the composition of copper in this alpha you want to find out. So let us say if we cool this below the solvus line, say at this temperature, we are cooling at this temperature. Okay, so here when this alpha is getting cooled, so alpha within itself only is trying to form a new phase, a new solid phase, the alpha saturated. Why I am saying this super saturated alpha? Because this alpha, this solid solution, this solid, it is trying to form a new solid phase within itself only. So within this alpha, it is forming this saturated alpha. See here, if you have the composition here at 4, I am taking this temperature here, okay, at the composition of 4% of copper. Here we are talking for this 4% of copper. So here the maximum copper percentage in this alpha is how much? 4%, and we are cooling it below the solvus line, as the equilibrium composition of this copper, actually how much? It is very less than this 4%, is actually 0.5% of copper. So how this alpha is going to decompose? So alpha is going to decompose as, on this solvus line, this alpha is become the saturated alpha, this alpha becomes the saturated alpha, and whichever the extra copper in that is coming out of this matrix and precipitate as this theta. Please remember what I am saying. Actually this is the precipitation transformation or solid state precipitation here taking place. That is, at this particular composition of alloy, that is 4% of copper, near to this, see, we are cooling it below, this solvus temperature, is this solvus line, and the equilibrium composition of copper is how much? Is very less than this 4%. So where this extra copper in that alpha will go? So it will come out from this alpha matrix as the theta, which is the precipitate, and this precipitate will be along the tri-junction boundaries, tri-junction grain boundaries, like this. So like this alpha is going to precipitate and grow, isn't it? As on the grain boundaries, this theta is going to precipitate. So this precipitate is going to what? It will create the resistance or obstacles for the movement of dislocation, and then when there will be the obstacles for the movement of dislocations, definitely the strength of the material increase, because we have to provide some extra stress to get it deformed. So in this way this precipitation reaction, actually this is the precipitation transformation, you can say, or this is the precipitation reaction, very important. That is, alpha is decomposes to form this alpha plus theta, where this alpha is actually super saturated alpha, and this is on the solvus line, that is a saturated alpha, and the remaining alpha, is coming out, so remaining copper in this alpha is coming out actually with this theta, which is a precipitate, which will grow along the grain boundaries and which will increase the obstacles for the movement of dislocations, and which will results into the strengthening of that alloy. So in this way we can increase the strength of this non-ferrous or this aluminum alloys. So dear students, so actually this is getting after the quenching only. See, no doubt we are cooling this below this solvus line. So in equilibrium cooling also, if you slowly cool this alpha, then only also we are going to get the alpha plus theta here, isn't it? So whether you cooled it from here or you cooled it from here, anywhere you cooled with the any whether you fastly cooled it or you slowly cooled it, the results are same, that you are going to get this alpha plus theta. But see here, to understand again why only quenching, why we are quenching that alloy only, not slowly cooled. So let us see the next. So see, for that, why quenching only, the question comes in our mind, that why quenching only. So अगर हमने स्लोली कूल किया तो भी क्या मिलेगा आपको, थीटा अल्फा प्लस थीटा ही मिलेगा. Whether you quenched it or fastly cooled, again you are getting the same, that is alpha plus theta. So why to quench, that is the question. So for that, let us we will try to understand by the TTT diagram. For this TTT, for this reaction alpha gives alpha plus theta, that is our precipitation reaction. So here is our T solvers I am having, because below that only we are going to quench it, and above T solvers there will be the pure alpha, isn't it? And so everything above it is what, alpha. Above T solvers, see, we are taking the range of, so this is the solidus line and this is the solvus line. So here is our supersaturated alpha is there, and we are taking this range only to understand why. Because see, above it, above this solidus, it is going to be in the liquid stage, isn't it? Liquid plus alpha. But we know that heat treatment is basically done for the shaped object. For that reason, we are using the temperature in between, or we are heating this alloy between this solvus to solidus, between the temperature of T solvus to T solidus. Please keep it in mind, because heat treatment is done always on the solid phase, on the shaped object. That is the reason. So above this, so we are cooling it below this, no? So below this solvus, so it is going to be as in solid state, and of course because we are cooling it. So above this everything will be alpha. So this is alpha, and say when we cool, we get this C curve. So this is the start of theta, this is the finish of theta. Of course here is also this alpha plus theta, here is also alpha plus theta, but it is in finished manner, and here this alpha plus theta, isn't it? Now see here, there are the two things. What I am saying, why we need to quench. Suppose if I am doing the equilibrium cooling, like this slow cooling, isn't it? And for rapid cooling, to bypass this nose of TTT curve, I have to quench it with little faster rate. And what I am doing after quenching, what is the process? We are keeping it for a particular time, that is the aging time, isn't it? So here we quenched. So this is of course T solvus, sorry, this is temperature at around, say I am taking from the 550 degrees centigrade. So here I am cooling it. So either I am having this slow cooled alpha, and this is the quenched alpha. This is the quenched alpha, then it is undergoing the aging. So here also we are getting what? Alpha plus theta, and here also we are going to get the alpha plus the theta. But see here, as you are very intelligent peoples, so you can see here, this transformation is actually occurred at the higher temperatures, and this transformation is occurred at the low temperature, please remember. And we know that when these transformations are occurred at the low temperature, there will be faster nucleation, And how is the growth? Slower growth, very important. And when we have this transformation at higher temperature, you know higher temperature पे क्या होता है? There will be the slower nucleation but faster the growth. So see here, if I quenched it at this high temperature transformation rate, so what will happen here? The growth of the nucleation will be this, the nucleation will form very slowly and it will grow, but that will be, it goes in a coarser manner. But see here the number of nucleation centers are more because faster nucleation there, and as the timing for growing of these nuclei are very less. So what you can see here, they will be many numbers but not grown completely, isn't it? They are many numbers but not grown completely. So we are getting here the fine precipitate of theta in this reaction, isn't it? Here the precipitate theta will be coarser. So as we know that the fine structure is always gives the maximum strength and hardness than the coarser structure. Please remember it. That is why. So देखो, अगर हमने अल्फा को इक्विलिब्रियम कूलिंग भी किया तो भी अल्फा प्लस थीटा ही मिलेगा, that is precipitation reaction. But why we need to quench? When we quench it in this fashion, there are more number of nuclei that is formed and they are having slower growth rate. So definitely finer structure of this precipitate theta is dispersed in the matrix of this aluminum, isn't it? And that will give us the maximum strength and hardness. So of course यहाँ तक को clear है. So in aging the hardness is increased. Now the thing is that after this peak hardness, the hardness goes on decreasing. So dear students, so after this point, after this time period, this precipitate theta is becoming coarser and coarser. ये क्या होता चला? So शुरुआत में क्या था? ये grains थे. There was a fine precipitate of this theta. Now again, if you pass certain time again, this theta is now started become coarse. And you know that when there is a coarse precipitate there, or coarse structure is there, little bit more bigger grain size. Here is a precipitate theta, so definitely the hardness is decreased. So dear student, this is the precipitation hardening, or this is the age hardening. So simple is what? This precipitate theta is creating the obstacle for the movement of the dislocation. We have seen in the dislocation theory. So whenever there will be resistance or obstacles for the dislocation, so to take out these dislocations, we have to apply the more stress, the more load. Ultimately what? Our alloy. कौन सा अलॉय? एल्यूमिनियम कॉपर जो अलॉय है वो क्या हो रहा है? हार्ड हो रहा है. उसकी स्ट्रेंथ एंड हार्डनेस क्या हो रही है? इंक्रीज हो रही है. Now that we want, that is the purpose of heat treatment, to strengthen, to harden the material. So this is the precipitation or age hardening process. Thank you so much.